for some reason, whatever it is, like more like rare, stronger flares happen at the limb. Well, hello everybody. So here's me. Like, if you were wondering why there were not many videos recently, well, this is why. It's because I've been working on this for the last 2 months essentially, but in the last couple of weeks especially intensely. So I've spent like 10 hours per day grinding in front of a computer, so that's why I honestly wanted to finish this so bad that I haven't done anything else, honestly. So yeah, I'm recording this on June 11th. So I've submitted this paper to the MNRAS letters yesterday, as you can see here, and I've also submitted this to the preprint server, but it's not up yet. So I'm gonna wait until it's up, and I'm gonna link the paper in the description when it's up, so you can read it right away, pretty much, when this video will come out. So yeah, but let's talk about the contents. So as you can see, we're talking about strong solar flares that are X-class, essentially. And well, if you remember, I taught you how do you read a scientific paper. Well, how do you do it? Well, first you read the title, obviously. Then you read an abstract. Then you read what? Conclusions, right? The final chapter. And then you read like whatever is you're interested in, like if you have any questions remaining. So let's do it actually. So I'm not gonna actually read it out loud because I know it takes a lot of time. So basically, what are we doing here? Okay, let me actually start with sort of a background info, because it's not very informative what you can read here. I mean, it's very informative, but the purpose of this video is actually to give you background info and kind of summarize, because you can read the paper yourself, and I would actually urge you to do it, but let's talk like meta stuff, right? So there is an idea. It's called Earth-facing solar quiet, right? What it means is that apparently, supposedly, anecdotally, the sun doesn't really flare against the Earth, right? So when the sunspots are like directly in front of the Earth, near the so-called central meridian on the sun, actually, like near this line, right? Near this central meridian, it doesn't flare as much as it does at the limb, the very edges, right? Like as you can see here, it's an X flare on September 8th, 2017. Back when Oumuamua appeared mysteriously, as you can remember. So yeah, so there is an idea that more flares happen at the limb. And basically that was the motivation for this research. So I said, well, we can actually test this, you know, we can actually look at the flares and see if they are more frequent at the limb. And it's actually not something completely novel, like people have looked into this quite a lot actually, not as much as north-south, for example, asymmetry. So here I talk about three types of asymmetries, right? One is disk versus limb, so roughly speaking center against the edges. So where are more flares? Is it at the edges or at the center? That's one type of asymmetry I considered. Another is north-south, so is it more flares in the north or is it more in the south? And the third one is east to west, right? So is it more flares in this half rather than this half, or vice versa, or is it equal, etc., etc. So these are the three types of asymmetries I considered. And I found something interesting, or at least I think I did. So at first I was a little bit disappointed, I have to say, because I've expected actually this effect to be true. Like I've expected more flares at the limb than at the center. But if you look at the actual data that I got, so, well, okay, there's also an issue of limb flares. Let me actually talk about this for a little bit before we go on to do anything else. So, as you know, probably, flares happen in coronal loops, usually. So, these are like the plasma loops that kind of link the sunspots of opposite polarity, right? So the plasma can just bounce back and forth as these magnetic mirrors of stronger magnetic fields exist there. And so when the current loop breaks somehow, you have the flare, right? It's what the so-called mainstream science calls so-called magnetic reconnection, which is BS, of course. It's just the surge of a current. I mean, not the surge of a current, it's rather the breaking of the current, which releases the energy, all of the magnetic energy, right? Li squared divided by 2. But anyway, so what this means is you have a lot of flares. So you can see I've divided the sun into this 20 by 20 grid. In my program, I can actually manipulate this. We can reduce it's actually the X factor. You can see it, it's kind of broken now. So I kind of manually adjust this. We can adjust the radius. You see, so for every picture of the sun, of the solar flare, I was doing this manually, and then I was putting the numbers into my table. The numbers being where do we have the flare, which longitudinal and latitudinal bin it corresponds to. Here it's in longitude 1, 2, 3, 4, 5, 6, 7, 8, and -2 actually, right? Roughly, it could have been. You could have argued that it happened at 7 -2, but regardless. So the loops they're actually situated above the photosphere, right? Which means that in this very last bin, you can sometimes see the flare happening behind the disk, on the other side of the sun, because you can still see the coronal loops towering above the surface for a little bit, but effectively it kind of inflates the number of flares at the very edge. So I had to remove that. So I had to again track whether the flare actually happened on the sun. So I've actually looked at the active region position. So if the sunspot actually is no longer seen, then I was discounting that. I didn't count this as a limb flare. I just completely ignored it for the purpose of center to limb counting anyway. For east to west, I did count it because, well, there's apparently supposedly equal number of these occulted so-called flares, or rather flares from occulted regions that departed the sun or have not yet appeared on the eastern side, right? So I did count this for these purposes, and for north-south as well, because again, they should be uniformly distributed, so there should be equal numbers of the ones that we see from behind on this side and on this side, right? But for center to limb, I discounted these flares. All right, so with that out of the way, so I've arrived at a few lists, as you can see. So I have a full list that counts everything that was registered by the GOES radiometer, right? The GOES is the satellite. It was geostationary Earth observing satellite or something like that, or whatever. I don't know the correct abbreviation, but whatever. So yeah, but it's a standard, right? The GOES 1 to 8 angstroms, the so-called long bin, they have is the standard for counting the flare class, the flux in this range, right? So we have 305 flares, each of which I manually processed. I manually processed like this and counted where it happened essentially. I've also looked, as you can see, at the duration of the flare, the peak flux, that is essentially the class of the flare, let's say X 3.0. It means that we have 3 times 10 minus 4 watts per meter squared. That's the flux of energy in this range that we talk about. And I've counted the integral flux, which means over the duration of the flare, what is the total energy emitted, or rather absorbed by the detector, right? Yeah, and then we have these two lists, B and M. B means behind. So here I've eliminated all the flares that definitely happened behind, in these occulted regions, right? And M means like maybe, which means that you could argue that it happened behind, but equally you could argue that it happened kind of here, because as you can see, like the flare is actually big, so it's kind of sometimes somewhat arbitrary whether you count it as behind or not behind. You know, like it's when it's at the very edge, like it's very 50-50. You know, there is actually a paper, and I cited here, this Kruker 2015, that actually even like brings up some classification of the flares that are kind of right at the very edge. It's very very like subtle, you know, like sometimes it's because, you know, the sunspots are also depressions in the photosphere, so sometimes it looks like it's behind, like, I mean, it's difficult, all right. So what do I have for this M list is like maybe. So here I eliminated even those flares that maybe happened behind, so it's the like the maximally conservative list out of all right. And then I subdivide these, like it's a temporal breakdown. Like what do we have during the solar minimum, during the solar maximum, during the rising phase, that is from minimum to maximum, then falling phase from maximum to the next minimum, then odd cycles, that's 22 and 24 here, even cycle, I'm sorry, odd cycles are 23 and 25, even cycles are 22 and 24, right? And by the way, like speaking of the flare list in the first place, I've only worked with the flares from September of 1991. Why? Well, exactly because I needed images. And only the images starting from, again, roughly September 1991 are available when we have the Yoko satellite. You can actually access the archive somewhere here, like here, yeah. And by the way, all the data that I have is here, and you can open the link. You have all the imagery, so you don't have to go and search for it on your own. And you have my last final table with all these flares and with some of my comments as well. It's like an Excel table, XLSX format. Yeah. So what did I found? Well, firstly, there is center to limb asymmetry, but as I've said, I was slightly disappointed because it's not as pronounced as I hoped it is, right? So in terms of, for example, flare number, so these are so-called asymmetries. They're defined as such. I'm not gonna spend a lot of time discussing this, but basically the bigger the number is, the bigger the difference is between, for example, the number, the duration, peak flux, and integral flux. Here it's the center to limb differences. Here's the north and south. North is positive, south is negative. And here it's east and west. West is positive. So as you can see, in terms of number, the most conservative M list, where I've eliminated all these, like even maybe, in air quotes, behind the limb types of flares, we have zero. Exactly zero asymmetry. So exactly equal number of flares at the center and at the limb. So that's why I was disappointed. So it seems like the distribution of the flares in terms of numbers is exactly uniform. Again, like if you discount, the flares that maybe actually happened on the disk, then you have a slight asymmetry in favor of the limb, right? But when I eliminate these flares, we arrive at zero. So yeah, so it turns out that exactly equal amounts of flares happen at the center versus the limb, the edges, right? So there is no such thing as Earth-facing quiet, at least in terms of X flares, at least in terms of their number. However, there is a difference in terms of duration. You see the limb flares are slightly, they're slightly longer. And it's the mean number. And the flux, peak flux is slightly higher as well. And the integral flux is slightly higher. I actually give the numbers in percents here in the results. So the mean peak flux of limb flares is around 18% higher with respect to the disk flares. Their mean duration is 5% higher, and the integral flux is around 13% higher. So they are kind of different, you know. But as I've said, it's the mean, right? but what about like the general population, the general distribution? Well, I have a histogram somewhere here. So these are, so on x-axis we have the peak flux, so that's x something, you know, like this is x5, for example. And on the y-axis is how many of them, right? So we have, this is the disk flares at the center, and this is the limb flares at the edges. So as you can see, at the edges we have more frequent, and it's a peak flux, right? As I've said. At the edges we have more of these stronger flares. There are like only a few of them. You see, it's one, so it's one of this, one of this, one of this, and the division is 0.1 here, the step. But there's more of them, as you can see. So we have some very strong solar flare, only one, right? At the center, like there's a couple of these, etc. But in the limb flares, we have much more of these stronger ones. So these rare outliers seem to be driving this effect. So for some reason, whatever it is, like more like rare, stronger flares happen at the limb. I don't know why, like no idea. Then again, we have during the solar minimum, and this is kind of the main discovery, if you may call it that, of this paper, is that during the solar minimum, we have significantly more flares. Like 2/3 of all the flares happen at the limb, at the edges. And not only that, they're also, actually they're slightly shorter, as you can see. Should have indicated that here. They're shorter by 32% on average. However, their peak flux is much higher. How much is it? You can, like, whatever percentages I have here, you can recalculate using these expressions, by the way. Like, I use these asymmetries. They're like a dimensionless unit, just for simplicity, because I can, you know, compare apples to oranges using it, essentially. Like, I can have a single metric for all the parameters. And it's introduced like this. So, yeah, so, and they have a higher peak flux and integral flux. So the peak flux is higher by 32%, and the integral flux is higher by 16%. But again, it's a mean. So, but even the number is higher, right? Actually, if you count the, I mean, it's both the numbers are higher and each flare is stronger on average as well, with respect to the disk flares. So this is kind of the main discovery that I have here, that during the solar minimum, 2/3 of the flares, that's not a lot of flares, honestly. I mean, it's the minimum, right? So we have 37 in the full list, or 32 in this maximally conservative one, but it's there. And the proverbial statistical significance is 5.5%. I mean, obviously the classical limit, not the limit, the threshold is 5%, right? When you have the probability, it's essentially the probability of getting this distribution from a uniform case. So if we assume that the flares happen equally probable for a limb and a disk, like what's the probability of getting such skewed statistics that we have? And it's 5.5%. And it's a binomial test, that's how you get it. But usually the threshold is 5%. If the probability is lower than 5, then you claim it's statistically significant. I never say these words in the paper, by the way. In fact, I'm kind of mocking the statistics throughout the whole thing. So I deliberately formulate things as they are, rather than as they should, like they usually are formulated, that, oh, it's statistically significant. But of course, you know my position on statistics. It's a scam, essentially, to basically convince people of whatever you want to prove, you know. But yeah, I didn't do that here. Like, I was just doing honest reporting of what I found. Like, I don't think there is a big difference between 5% and 5.5%. And I mean, it's completely arbitrary, right? You can say, well, why don't we claim that less than 10% is a significant outcome, you know? because 10% is a very small probability, you know. So I don't know, like whatever. So yeah. So yeah, the probability of this effect occurring just randomly from a uniform distribution is only 5%, 5.5 to be precise. And it's kind of the most significant result of the paper, really. And actually, like, there's an Easter egg. It's a true story, by the way. I can even show you the picture, probably. No, I can't. It's somewhere else. But yeah, I have a picture in my, literally in my notebook, which says that if you discover something, call it Vinny effect. So that's what I'm doing. Maybe I'll actually post it when I'm gonna edit the video. I'll show you the picture from my notebook. Okay, yeah, I've also found the north-south asymmetry, but it's well known in the literature, so I didn't really found anything new. Necessarily, you can see the probability is incredibly small, so it's actually there, like no doubt about it. North-south asymmetry is actually there, and it's confirmed by many other studies. It means that in the recent cycles, south has been much more active. And it has to do with the general asymmetry in the polar fields of the sun, where the southern polarity is much stronger. It is what it is. But like, it's not always the case. Like, there have been suggested, I think I make a quote here. It has been suggested that there are like a longer cycles, like maybe this quote. Actually, no, not this one. Wait. This paper talks about essentially the independence of the solar north and the south, like they evolve separately essentially. But I have a paper that says about the longer cycles. I can't find it, but anyway. So yeah, longer cycles seem to be existing. By longer, I mean like 40 years or whatever, something like this. So it's not always the south is strongest, that's what I'm saying. Maybe actually in this cycle we'll see a stronger northern part, which is actually what we see. As you can see, cycle 25, we haven't had a lot of flares, some only 16 X flares, but most of them happen in the north actually. Oh wait, it's this glim. Wait. Okay, I'm completely retarded. Actually, north-south, it's completely equal. It's mostly limb, actually. Never mind. Okay, I'm falsified by my own paper. So it's mostly the limb flares in cycle 25, but north and south are exactly equal. But as you can see, like previously, the south was dominant, right? But now it's not the case, at least so far. So, and the dominance of the south seems to be waning, right? So maybe it's going to be the first cycle with a stronger north. We're going to see. I mean, you can probably make predictions based on the actual observed polar fields already, but I didn't bother. Like, it's an observational paper, you know. I just look at the flares, I document where they are, and I report what I found. Like, I didn't make any hypotheses here, except for the one that all of these asymmetries seem to be connected to, again, this large-scale solar magnetism. And yes, what about the east-west? Well, it seems that there's slightly more western flares, slightly more. You see the 8,000th is the asymmetry measure, where in terms of percent, it's like 4% more of western flares in terms of numbers, right? So yeah, so the idea that, I quote, Earth kills sunspots, as Maunder has written in his stupid book, is a stupid idea. So apparently there's actually, if anything, Earth kind of boosts sunspots in the sense that there are more flares in the departing side rather than the arriving, the ingressing side, right? So yeah, an interesting thing, but not a lot, right? 4% is nothing essentially. So that's why we have these p-values are very high. So essentially, the probability of getting whatever we observe in terms of numbers is pretty high from a uniform distribution, that is. So it's not significant, these differences. 4%, I mean, it's kind of abysmal in the first place. But, however, during the solar minimum, it's different. As you can see, the west dominates again. What's the exact measure? Let me see. Wait. Yo, I didn't write it here. Oh, yeah, I did. So 31% in terms of number, I think. Is it number? No, it's duration, peak flux, and integral flux. I didn't actually write the percentage for the number, but it's pretty big, as you can see. Where is it? East-west. Minimum 0.136. So it's like maybe like 25% more. Like I can't calculate it in my head, but it's a lot actually. A lot more flares in the west during the solar minimum. So yeah. So basically these are the main findings. There are more flares at the limb, actually not more flares, same amount of flares at the limb, but they exhibit these stronger outliers. For some reason there's more of them. There is more flares in the south, but it has been known. I just kind of confirmed it. There is more flares in the west, and all the asymmetries are much more pronounced during the solar minimum. Why? Well, because of large-scale magnetic structuring. So during the maximum, the sun is in like a very chaotic state, right? The poles reverse, all kinds of weird stuff is happening. But during minimum, we have a very, very highly structurized field structure, forgive me for tautology, and all these asymmetries are more pronounced. What do they mean exactly? How do they happen? Like, what's the exact physical mechanism? Well, that's a good question. So, a hypothesis is that the flare may appear brighter at the limb, exactly because maybe the flare, like, emits light differently under different angles. It's very possible, right? That is called anisotropy, the difference in, like, depending on the angle of observation. And seems to be the reason for this. But I'm not sure. I have no idea. Luckily, we have two instruments that are designed specifically for this, to stereoscopically image the same event from different vantage points. One is in Earth orbit, it's MISOLFA instrument, and another is Styx instrument on board of the solar orbiter, which orbits the sun and not the Earth. So it's going to be someplace else when the flare will happen. And I actually anticipate the results from these guys. Hopefully they'll find something interesting. And we can falsify whatever I said regarding the flare anisotropy. So yeah, it's an ongoing research, as you can see. But looking from the Earth, I just observe what I observe and I report it to you. Well, hopefully it was interesting to you. I know I've ranted for quite a while, but then again, I've spent like 2 months sitting at my apartment, not talking to anyone, just grinding this stuff. I wanted to say a different word. And yeah, so if you want to discuss this, well, you're welcome. I would gladly do it. Yeah. So, thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.